Okay, so I think this is working again. Hopefully it will continue to work for the duration of our lecture. All right, so now we're getting to the good stuff, right? We're talking about calculus as it applies to polar coordinates, right? So we're going to take a look at tangents with polar coordinates, and then we're going to take a look at area with polar coordinates. Those are the two main applications that we're going to take a look at, okay? You can do things like find arc length for, like how long is a petal, how long is one segment of Archimedes spiral, but sometimes those integrals are really hard to do by hand. So I just want us to know that it's out there, but that's not going to be something that we necessarily cover. But we're going to take a look more at like how do we find slope as it applies to polar equations, and how do we find area as it applies to polar equations, okay? So let's get started with tangents of polar coordinates. So if you want to find the slope of a given polar curve, here's the formula that we're going to use, okay? So to find dy dx, we have to find dr d theta times sine theta plus r cosine theta. And that's all going to be over dr d theta cosine theta minus r sine theta, okay? Now, things that this allows us to do. If we can find the derivative, then we can find the slope of a polar curve at a specific point. We can write equations of tangent lines or normal lines to the polar curve, and we can determine the location of horizontal as well as vertical tangent lines. Okay, so those are the applications we're really looking for here. So let's jump right in with example number 1. Okay, so it says given the polar curve r equals 4 cosine 3 theta, and we're going from 0 to 2 pi. Okay, so the first task is name that shape. Okay, so name the shape. Let's think about some important features of that shape, and then we will go from there. All right, I hear one for a rose curve. I second that. It is a rose curve. How many petals will we see?
We will see 3, or yeah, 3.
We'll see 3. If we go from 0 to 2 pi, though, technically we're asking ourselves to draw 6. Just the first 3 are on top of the second 3. Okay, cool. So we've got a rose curve. I know there are 3 petals. Okay, and what is the length of each petal?
2.
I hear a 2. Anyone else? I hear 4. So is it 2 or is it 4?
Since it's not squared, is it 4?
Yeah, it's not r squared, so it's just r. That number in the front tells you how long the petal is going to be, okay? So this is going to be 4 equals the petal length.
If it was a circle, though, the diameter would be 4, and the radius would be 2.
Yes, yeah. Okay, now here's where the symmetry comes into play, because again, I don't want to set up a table every single time I want to graph, right? So I know there are 3 petals. I see the cosine, and so I'm thinking that it's got symmetry about theta equals 0, okay? Now what that means is my petal, like the first petal, has to be along that theta equals 0 if I'm going to have symmetry about it. So I know I'm going to start at 0. I'm going to go 1, 2, 3, 4, and I'm going to have 1 petal like that. that means that the other two petals are going to be in quadrant. Oh. We're going to be down here. We need a length of 4 and then 4. Okay. Now, if it were sine instead of cosine, we would end up with 6 petals. And we would have to go from 0 to pi, or 2 pi to get all 6 petals. All right, so there's our shape, there's our sketch of the graph. And now our question is find the slope of the curve at theta equals pi over 4. So we're going to need that formula up here in the blue, okay? So since this is our first time through, let's write the formula out and then we'll fill in what we need in the second line, okay? So we've got dy dx equals dr d theta sine theta plus r cosine theta dr d theta cosine theta minus r sine theta. Now let's fill in what we have given our equations. So dr d theta is going to, what's the derivative of 4 cosine 3 theta?
Sine.
Negative 12 sine 3 theta.
Yep, negative 12 sine 3 theta, right? Because we got to use chain rule. And then I need a sine theta, because that's the formula, plus r cosine theta. Okay. Now I'm going to do the denominator, negative 12 sine 3 theta cosine theta minus 4 cosine 3 theta sine theta. Okay. So now that we have this, you can do one of two things. Some people like to simplify first. Some people like to just plug in all of their unit circle values right away, okay? I found that students tend to like to plug in all the values right away because then they're just working with numbers rather than working with combining different angles and such, okay? So we're gonna go ahead and we're gonna replace pi over 4 everywhere we see a theta, and we're gonna find the value for that angle in the same step. Okay, so I have a negative 12, that stays. Sine of 3 theta is really the same thing as saying sine of 3 pi over 4. Does that make sense? Then we have sine of pi over 4 plus 4 cosine 3 pi over 4 cosine pi over 4. Negative 12 sine of 3 pi over 4 cosine of pi over 4 minus 4 cosine 3 pi over 4 sine pi over 4. Okay. All right. Let's fill in our trig values now, okay? So I have negative 12 Sine of 3 pi over 4 is root 2 over 2. Sine of pi over 4 is root 2 over 2. Plus 4 times negative root 2 over 2 times root 2 over 2. And then negative 12 root 2 over 2 root 2 over 2 minus 4 negative root 2 over 2 and root 2 over 2. Now, some of you folks have not been putting that unit circle on your cheat sheet. I would highly recommend that you put that on there, okay? I'm not saying that I don't believe that every single one of you have it memorized, but in my experience, most people don't have these memorized. So don't waste your time trying to figure out what these are. Just get it on your cheat sheet so you have all of these values, okay? And now from here, it is a lot of simplifying, and all of this is stuff that you should be able to do without a calculator, okay? So simplifying from here without a calculator is definitely an important skill. I like to reduce fractions first before I multiply anything out. It just keeps the numbers a little bit smaller. So for example, I know that in this first set of fractions, 2 times 2 is 4, but 4 into 12 gives me a 3 in the front, okay? Then I look at the second terms and I see a 4 on the outside and a 2 and a 2 on the bottom. So 4 and 2 are going to reduce to 1. I do the same thing on the bottom, so I'll get negative 3, and then those will go away. All right. Let's take this now that we've reduced it and see what we actually end up with. Usually after that simplification step, it gets a lot easier. So I have negative 3 times root 2 times root 2. What does that give me?
6.
Negative 6.
It gives you negative 6, yep. So I get a negative 6. And then in the next step, I have minus 2. And then on the bottom, I have negative 6. And then I have plus 2. Right, so that was kind of the worst step, was once we filled in all the numbers. It just looks like a lot because you have a lot of roots in there. But if you reduce things, like, they do generate nice numbers, okay? And so when we simplify, we get negative 8 over negative 4, which gives us a slope of 2. All right. So what that means is, if I had drawn my diagram a lot more carefully, okay, if I go to pi over 4, wherever that point is, if I were to draw a tangent line, the slope of that tangent line would be 2. That's what we found. Okay. All right. Any questions on example number 1?
Yeah, I just got one question.
Sure.
Is R the same thing as f of theta?
As what?
As f of theta? I tried attempting the quiz yesterday, and I didn't, like, it was asking for like the slope and stuff like that, so I just did a quick look online, and it gave your formula pretty much, but instead it said f prime of theta times the sine plus f of theta times the cosine.
Yeah. R is really R of theta.
I thought I was going to have to delete the whole thing.
Okay. So let's try example number 2, okay? So I'm going to give you a couple minutes to look back at your notes from 13.3, identify the shape, and sketch a graph of r equals 2 plus 2 cosine theta. Okay. All right, so when we take a look at this equation, we notice that we have an a plus b cosine theta. So automatically, we should be thinking this is in the family of the Lima song, okay? Oh, shoot, that stopped sharing. Hold on. All right, there we go. Sorry. So we're thinking that it's in the family of the Lima song. We're just trying to decide which one of those it is. And so when we take the orange number and we divide it by the blue number, we get 1. And so that should tell us that we end up with a cardioid. Because a over b equals 1. Now I know that this one is cosine. So because of the cosine, I know the symmetry is around theta equals 0. Okay. So kind of cool if you like nerdy things, but if you take your a plus b, right, so 2 plus 2 is 4, okay, that actually, for the cosine one, gives you the radius that you go out at 0. So 2 plus 2 is 4, so I go 1, 2, 3, 4. That's how I can get that point maybe in a shortcut way, okay? Now, if it was 2 plus 3 cosine theta, then I would have to go out to 5 because 2 plus 3 is 5. So the other thing that those numbers are helpful for is they give you what it's going to be at pi over 2 and 3 pi over 2. So at pi over 2 and 3 pi over 2, we're going to be at 2 and negative 2. Okay, so I can see sort of that the right-hand side of the cardioid. And then because it's a cardioid, there's no loop, it's not dimpled, it's not convex, but it makes a nice little heart, a sideways facing heart. Okay. And again, you can make a table of values, but make sure that you are picking nice values so that you're not creating more work for yourself in a bunch of random decimals. Okay.
So you can add those A and B to find your first point?
That does help you find the first point for cosine, but not for sine. For sine, it would be like the second point.
Okay.
Okay. All right. So then part B says determine the slope of the curve at theta equals pi over 6. All right. So we're going to go ahead and write out our formula. All right. So I know I have dr d theta as the first term. So that's going to give me negative 2 sine theta. And then I have a sine theta. Plus r, which is 2 plus 2 cosine theta times cosine theta. And on the bottom, I start the same way, but instead of a sine, it is a cosine. And then I have the r again, but instead of a cosine, it's a sine. And it should be a minus sign connecting those two on the bottom. Okay. Again, I think that most students tend to like plugging in the numbers, like your unit circle values, right off the bat, but you don't have to. You're welcome to kind of simplify. You'll get like a sine squared and a cosine squared. But I think it's harder if you're trying to find an actual number to simplify first, okay? So let's fill in all our unit circle values. -2 times 1/2 times 1/2 plus 2 plus 2 cosine of that is √3/2, and then √3/2. I'm going to do the same thing in the denominator, -2 times 1/2 times √3/2 minus 2 plus 2 times √3/2 times 1/2. All right, well, let's start reducing and see what goes away. So I know that this 2 and this 2 will go away, and I can kind of do the same thing on the bottom. Let's see, this and this will get canceled out by this 2 in the denominator because I distribute. And same thing here, this 2, and that 2 will all cancel out. That gives me -1/2 for the first term, plus I'm going to distribute here and distribute here. I get plus √3 plus 3/2. I do the same thing in the denominator. I get -√3/2 minus 1 minus √3/2. All right. So I think it's probably best to kind of combine like terms before we start to think about making like a common denominator. So what I mean by that is like this -1/2 and this 3/2 I could combine because they both have a denominator of 2. And then same thing on the bottom, I could say this one and this one I can combine into a single term, okay? So what does that get us? That gets us -1/2 plus 3/2 is 1 plus √3 over, on the bottom, I end up with -3 √3/2 minus √3/2 is -2 √3/2 minus 1. And these reduce. So really I have 1 plus √3 over -√3 minus 1, which if I factor the bottom gives me negative parentheses 1 plus √3, which is super nice because these reduce and I'm left with a final slope of -1. Okay. And again, my diagram is a sketch, but if I go back to my diagram at pi/6, and if I were to draw a tangent line, then the slope of this tangent line would be -1, okay? All right, so those 2 parts we saw in example 1. We named the shape, we sketched the graph using like what the equation has rather than using a table, okay? I know that a lot of the Calc 3 professors really want you to know how to sketch them based off of the equation and not tables. That's why I'm sort of preparing you for that, okay? And then for part B, we found the slope using the same formula that we did in example number 1, okay? So we're going to layer onto that, where we're going to now take a look at where the curve has horizontal tangents and where the curve has vertical tangents. So conceptually, let's make sure we understand what that means. All right, it's the same as when we thought about the parametric equation. So that concept is not different. Instead, the types of equations we're working with are a little bit different, okay? But a curve is going to have a horizontal tangent when the slope equals 0. In other words, just like we did in parametric, we're going to set the numerator equal to 0 and solve for theta. Okay. Now, if we think about what's going to be different for determining where the curve has vertical tangents, we want to find dy dx is undefined because a vertical line has an undefined slope. And that means we're going to set the denominator equal to 0 and solve for theta. Okay. All right, so let's take our numerator from above. All right, so the numerator that I'm going to take is this. Okay, so that is what we're going to set equal to 0. Right? So what am I going to set equal to 0? I've got -2 sine squared theta, because I sort of multiplied that sine theta and the sine theta, plus 2 cosine theta, I distributed that, plus 2 cosine squared theta. And we want to set that equal to 0. And we're setting that equal to 0 because that's how we find out where the slope is going to be 0.
Is this top part the same thing as dy over d theta?
No, it's not like parametric in that sense.
Okay.
Okay. And let's at the same time pull the denominator and write that for part D, okay? So we're going to need that denominator, and we can kind of distribute and simplify, and we're going to get -2 sine theta cosine theta minus 2 sine theta minus 2 sine theta cosine theta equals 0. Okay, so this comes from the denominator of what we set up above. All right, so in order to solve these equations, we got to know our trig identities. Okay, that's another thing that's been missing from a lot of the cheat sheets. Some of you are putting them on there and some of you are not, but a lot of you are using a lot of random trig subs on there. So please make sure that your cheat sheet has the information that you plan to use on the exam, and that those things should match. Okay. All right, so here we go. I'm going to go ahead in the part C. We're going to start with part C. And the first thing I'm going to do is I'm going to divide every single term by 2, including the 0 on the other side. So I end up with all coefficients of 1. And at the same time, I'm going to take this cosine squared and I'm going to move it to the front. So cosine squared theta minus sine squared theta plus cosine theta equals 0. Cosine squared theta minus sine squared theta gives you cosine of 2 theta. Okay. And another way that you could write the cosine 2 theta, and you could have made this substitution right off the bat, is you can write it as 2 cosine squared theta minus 1 plus the cosine theta that you had there. And our rationale for turning everything into cosine and cosine squared is so that we can factor it, all right, and then be able to solve for theta. So this factors into 2 cosine theta minus 1 and cosine theta plus 2. Nope, plus 1. All right. And I would, if you're not confident with your factoring, I would FOIL it back out just to make sure you got what you started with, okay? But once we have these, we can set up our mini equations, and we can get in the first one that cosine theta equals 1/2, and in the second one, cosine theta equals -1. And then, in order to answer our question, we want to make sure we get all the values. We need to make sure we get all the values that make these equations true one time around the unit circle. So this first one will give us pi over 3 and 5 pi over 3. And this second one, where's cosine -1, it will give us pi. Okay, so these are the theta values for which your horizontal tangent occur on this graph. Okay, now I don't think I made my diagram nice enough for us to be able to see these. But if you go back to pi over 3 or 5 pi over 3, so pi over 3 is like here, there should be a horizontal tangent there. At 5 pi over 3, there should also be a horizontal tangent. Okay. All right. So we're going to do the same thing for part D, right? Except the difference is we set the denominator equal to 0. And so we're going to approach this similarly. We're going to see what we can do to simplify, what kind of trig identities we need to simplify here. But right off the bat, I see that we have 2's and everything. So like I did before, I'm going to divide everything by 2. And I am going to get negative 1 of these and 2 of these, so -2 sine theta cosine theta minus sine theta equals 0. I know that 2 sine theta cosine theta is an identity, but one thing that is really helpful to us is greatest common factors, okay? So if I turn this into a 2 theta, it's not necessarily going to be helpful. So what we're going to do instead is we're going to keep what we have, and we're going to factor that sine theta out of both terms. And when we do that, we get sine theta. I get -2 cosine theta minus 1. Okay. Now I can set each piece equal to 0 and solve from there. So where does sine theta equal 0? Well, that's going to happen at 0 and pi. And this one gives me cosine theta equals 1 divided by -2 or -1/2. And where is cosine equal to -1/2? Well, I get 2 pi over 3, and I get 4 pi over 3. Okay. Now, you'll notice that we actually got the same answer for both the numerator and the denominator. So like we have theta equals pi, and we also have theta equals pi here. And if we look back at the diagram, I did not attempt to draw a tangent line for theta equals pi. Now, if we kind of zoom in, okay, at pi, the radius is 0. So at that point, is the curve differentiable or not?
It's not.
No.
It is not. That is actually the definition of the cusp, right? That's exactly what a cusp looks like, that it's not differentiable at that point. And so what that means is that it is not going to have a horizontal tangent there because we can't find the slope of it. And technically, it does not have a vertical tangent line there either because it's not differentiable. Okay, so that's where we need to be a little bit careful. Like, is there a cusp or a corner? Then we want to make sure, okay, that point should not be in our answer. All right. So we have then.
Professor, can you repeat that?
Can you let me finish my sentence?
Mm-hmm.
Okay. So at theta equals 0 and theta equals 2 pi over 3 and 4 pi over 3, if you drew a more accurate diagram, you would see that there are vertical tangents there, okay? And if you went to these two, you would find horizontal tangents. But the exception is at theta equals pi, where it's not differentiable. And if it's not differentiable, we can't have a horizontal tangent and we can't have a vertical one, okay? Does that answer your question?
No, I'm still a little bit confused for why can't we use the pi?
Because it's not differentiable. You can't take a derivative there. If something's not differentiable, like you can't take a derivative, there's no tangent line.
And maybe I'm missing that. Like, why is it not differentiable over there?
Because it's a cusp.
Okay.
Okay, so a cusp is an example of a type of point that is not differentiable. Cusps and corners and any type of discontinuity would be not differentiable, okay? I know it's a lot of Calc 1 stuff coming back. Okay, so once we have all of this information, okay, again, I think that's why the diagram is important, so we can kind of think about, does our answer make sense or does it not? And so if we have anything that looks like this, like right at that point, it is not differentiable. Or if we had a corner, at that point, it is not differentiable. Okay, so those are things that we need to remember.
So whenever it looks like that on the graph, that's the cusp?
Yeah, yeah.
A dimple would not be included in that, correct?
Why not?
I will take that back.
So anytime you see a place where you could draw more than one tangent line is possible, then we say that point is not differentiable, okay? All right, so I'd like to start the second section, see how much we can cover for the area. And then we'll make adjustments as necessary, but I think I'll stop class a little bit early, like 5 minutes early, so we can kind of talk about any adjustments we need to take, okay? So with the area of polar coordinates, all right, that is another common application of calculus to polar curves, all right? So let's start with what we know. We know when we first learned about integrals that if you have this curve, y equals f of x, and you had a bottom bound and a top bound, that we could say, hey, I want to find the area, and that's what this integral is all about. We integrate the function, we start at A, we finish at B, and that tells us the area between the curve and the x-axis, okay? So what's new is that because we don't have an x and y axis, right, because we're in polar, everything is about the angles that we start with, okay? So our bounds now represent the thetas, not an x value or a y value, okay? So when we have a curve, if a polar curve, if we want to find the area, we're going to take whatever angle we start at. So theta equals alpha, and that becomes our bottom bound. And books tend to use alpha, not A. It's alpha so that we know it's an angle, A because we know it's like an x value, all right? And then we're going to stop wherever that shape stops at. So theta equals beta, okay? So we've got our starting angle and our ending angle. And James, I think this is the notation you were talking about. Some textbooks and some instructors will use r equals f of theta. You don't have to use that. It's the same thing as saying r. But just so we know that r is a function of theta. And that r is what we put into the equation. So we have 1/2 r, and then we have to square it, okay? All right. So let's take a look at this first example. All right, it says find the area of the region bounded by r equals 2 plus 2 cosine theta. And so this is, as we saw in the last example, it is a cardioid. It is symmetric about theta equals 0. And I can sketch a quick picture. I tend to use the XY coordinates when I'm sketching, just so I don't have to draw out a bunch of circles. But if I wanted to do a quick sketch of this graph, I know that 2 plus 2 gives me the 4 out here. And then my A and B values tell me sort of like where it intersects here. I seem to have angered the technology gods, sorry. Okay, and then we end up with something kind of like this. Not differentiable there. All right, so we've got this. Not differentiable at the cusp. Okay. So let's set up this equation for our area. So area is going to be, I like to pull the 1/2 out to the front sort of right away, but you don't have to. Some people like to keep it on the inside of the integral. But I'm going to go 1/2 the integral from alpha to beta, and let's talk about those in a moment, of r squared. Mental note, when you have to square this r, you better FOIL, you better not distribute, okay? Now, this one is a pretty straightforward case in the sense that in order to generate the entire cardioid, I need to start at 0 and I need to end at 2 pi. I need to go around the unit circle 1 time, okay? So it's almost like 0 to 2 pi is our default in a lot of these situations. All right, we will take a look at situations where it's not from 0 to 2 pi, but it's not a bad place to kind of start if you're not sure. All right, and again, tomorrow we'll talk more about cases when it's not from 0 to 2 pi. And then from here, we can use ideas of symmetry. We can use trig identities. All right, so all those trig identities that we used in chapter 9 are probably really good to get on that cheat sheet for exam number 3 next week, okay? But I'm gonna go ahead and take half of this shape and double my area at the end. Meaning I'm going to find this area and then I'm gonna multiply it by 2. And because the cosine cardioid is symmetric about theta equals 0, I can actually say, hey, let's just integrate from 0 to pi and then double it. And that doubling cancels out that 1/2. So I don't have a coefficient that's a fraction anymore, which is kind of nice. And at the same time, I can FOIL. So I get 4 plus 4 is 8 cosine theta plus 4 cosine squared theta d theta. Okay. Now remember, this symmetry tells you how you can change your bounds. So if I had 2 plus 2 sine theta, I cannot just go from 0 to pi and then double it. I'll end up with, like, if it was the sine graph, I'd end up with sort of like this part in the purple. And if I double that, that's not going to give me the area of the whole shape. Okay. All right. So these kinds of integrals seem a little familiar to us. The 4 has no problem. The 8 cosine theta has no problem. The cosine squared is the problem. So instead of cosine squared, I'm going to write 1/2 times 1 plus cosine 2 theta d theta. Which is nice because this 4 and this 1/2 are going to reduce to 2. So I get the integral from 0 to pi of 4 plus 8 cosine theta plus, let's take this 2 and distribute it, 2 plus 2 cosine 2 theta d theta. Okay. Now at this point, I can combine some like terms. So 4 plus 2 is going to give me 6. And I could end up with 6 plus 8 cosine theta plus 2 cosine 2 theta d theta. And then every term I have in here is now able to be integrated. So we get 6 theta plus 8 sine theta plus 2 divided by 2 means this coefficient goes to 1 of sine 2 theta. And I'm going to plug in pi, and I'm going to plug in 0. All right, what does that give us? 6 pi plus 8 sine pi is 0, plus sine 2 pi is 0, minus 0 plus 0 plus 0. And so the area inside the entire cardioid is 6 pi units. All right, so we're going to stop here for today. We've got 3 more examples and we will cover those tomorrow, okay? I'm going to stop sharing my screen for a moment just so I can take a look at the calendar and see what we can maybe modify a little bit, All right, so I'm gonna stop this share. Okay. Okay, so here is our summer schedule. Take a moment to celebrate all that you already did and all that you already learned. But let's do this. Let's make quiz 9 due on Wednesday, not Wednesday. We will say Thursday at 9:30 a.m. That'll give us some time tomorrow to finish up 13.5. Okay. I'd like to, let's also bump quiz 10 to Saturday at 9:30. We can bump it more if we need to. The 6.5, 6.7, 6.8, I'm not sure how long those are going to take. So it's possible we'll make up time and we won't need to bump it again. But if we do run out of time, we can certainly be flexible with that deadline, okay? So let's kind of at least move quiz 9 and we'll take quiz 10, kind of see how Wednesday and Thursday go, okay? Does that sound okay?
Yes.
Yes, okay. All right. So that's it then. I would encourage you to start on quiz 9. You can do most of the problems except for maybe some of the ones towards the end where we didn't get to like the special cases of the bounds. But you should be able to do most of it based off of our work from Monday and Tuesday, okay? And then tomorrow we'll finish up 13.5. We'll see how far we get with the work and the moments of center and mass, and then kind of reschedule as we need to from there, okay? I'm okay pushing deadlines a little bit for this section because especially with the polar and parametric, those are ones that are going to come up again in Calc 3, whereas like the sequences and series don't really come up again until differential. So, you know, if you plan to go all the way to differential, we'll at least get an exposure to it, but make sure it's enough that you'll be able to find success in differential. Okay, so that's it for today. If you don't have any other questions, you're welcome to take off.